another supplemental PowerPoint or slideshow on DC generators. The one from Chapter 9 is reasonably short, so we'll talk a little bit more about DC generators here. Again, in previous classes, DC and AC, we have talked about generators in passing. Generator basically converts mechanical energy, some sort of force, whether it's a motor or wind propelled or hydroelectric dam, whatever. We use some sort of mechanical energy to turn our conductor through a magnetic field so that the conductor cuts magnetic lines of flux. The bottom bullet there with the little highlights is the key amount of voltage generated depends on the strength of the magnetic field, the angle at which it's the conductor is cut through the magnetic field, which the previous PowerPoint did a pretty good job of showing as it rotated through the the magnetic field. The speed at which the conductor moves, and then the length of the conductor overall within the magnetic field determines the the amount of voltage. We'll again quick look at an elementary generator, very simple single loop drawing. AC generators, I said before, AC is what's produced by all generators. In an AC system, we have slip rings and brushes that take the power off, and we get a standard AC sine wave from it, and showing as it goes, rotates through. We get again at point A here, or position A, 0 degrees. We're running parallel with our magnetic lines of flux, so we produce no voltage. At B, we're running at 90 degrees, so we produce maximum voltage. C again, we're back to running parallel, so back to 0. Again, 90 more degrees, we're at maximum negative, and then 90 more degrees back to 360, or back to our beginning 0 degrees, we produce AC. In order to turn it into a DC generator, we very simply add commutator and brushes, and it says a segment of 2 segmented insulated metal ring. Again, it basically is split halves. It keeps the power going through the same direction. So just like we had before with the AC sine wave, we go from 0 up to our maximum at 90 degrees, or at point B, back to 0. But then because of our commutator, instead of going below the 0 line and producing what would be a negative voltage in AC, or a negative reading in AC, we go back to producing a positive signal. And so we get pulsating pulsating DC out of it. One of the ways that we reduce the DC ripple is by adding in additional coils. Then it doesn't get a chance to go all the way back down to 0 before it continues back up. Multiple coils in a system create a much smoother waveform. The other thing we can do is add additional poles. So in combination, by adding additional poles and adding additional windings, we can make a reasonably smooth line, although we never get it completely smooth. And one of the things that limits us is armature reaction. Again, our main magnetic field shows here on the left in figure A. It's going from north to south. Our magnetic field is there. Around our conductors, we get magnetic fields. As they rotate through, it affects our main magnetic field because of the interaction between the two. Again, we learned in we'll say middle school or maybe high school about magnetic lines of flux and the fact that they do not cross. One of the ways to overcome armature reaction is with compensating windings and interpoles, and we can improve our armature reaction that way. The other thing that we get out of it is motor reaction in a generator. As the induced current increases, the reaction force increases. More force has to be applied in order to keep it moving. And so, again, what may be initial force to get it started, once we have some magnetism being built up, we need a little extra force to overcome it. Our major losses in a generator are copper losses. And again, we've talked about I squared R in DC and AC. I squared R heating losses are throughout the windings because the windings are obviously made of copper. There are friction losses due to heat in the bearings. And then there are eddy current losses. Eddy currents are those as the magnetic field tries to go back and forth. It creates heat as those magnetic domains bump into each other. And then there's hysteresis loss, which we talked about hysteresis in previous classes. Hysteresis is the cause or effect when things are changing directions continually. They generate heat in the magnetic cores as well. One of the ways that we prevent that is by using laminated cores. That helps to prevent some of our hysteresis loss and our eddy current losses, but it doesn't do 100%. So looking at a simple practical DC generator, again we have a drum type armature with slots, and our windings are wound in the slots. Again, it depends on whether we use lap windings or wave windings. And the book will talk about that a little bit. We talk a little about DC excitation, a way to increase our overall output. They can be self-excited, or we can have external excitation. Residual magnetism can always be an issue as we're rotating through, and again that has to do with our hysteresis and our eddy current losses. Then we talked about our classifications of our generators, series versus shunt, and then also compound wound. The three basic types. Again, there's some advantages and drawbacks to each type. One of them we'll kind of look at on the next slide with output characteristics. And again, the book will talk about some advantages and disadvantages. Characteristics of a series wound generator is the output voltage continues to build up to whatever load current we have. The drawback here is if allowed to run without any opposition. Oh wait, sorry, that's a motor. Series wound DC motor running without opposition will run faster and faster and faster until it burns itself up. DC generator just continues to turn faster to give more output voltage, or can, until we reach the max. Shunt wound generator, the more load you add to it, the less voltage you get. So there's certainly a drawback there, and that's why compound wound are probably the most common. We have a nice steady voltage no matter what our load is asking for as far as power goes. So then kind of a recap here to talk about our components in a generator. We talked about the commutator being individual pieces of metal that are connected to our armature coils. They keep the help to keep the polarity always the same. We have our magnetic circuit. There's always an air gap between the armature and our field windings, so that there's room for it to turn. Kind of shows a field winding down here under B. Pole pieces and our field windings wrapped around them. Again, the pole pieces are work as sort of a core. Brushes. We talked about commutator and brushes. In E, we're looking at a brush holder here with spring for tension, so it holds it against the brush, and so it holds the brush tight against the commutator. And look at overall construction. Again, we have our couple of end bells on our frame, our armature, and our main field coils. Shows our bearing caps, air for cooling, commutator here for attachment of our brushes, and then a terminal box where everything comes out and is terminated. Again, the book does a pretty good job of talking about it, but this was just a recap on DC generators for electrical systems.